NDE methods, ultrasonic phased array, PUT, advanced ultrasonic technology for structural inspection. Overview of ultrasonic phased array. Ultrasonic phased array testing, PUT, is an advanced non-destructive examination method that utilizes multiple ultrasonic transducer elements, which are individually pulsed and controlled to steer and focus sound beams within a test object. This capability enables improved flaw detection, sizing, and imaging compared to traditional ultrasonic testing, UT. The method is widely used in industries such as oil and gas, power generation, aerospace, and manufacturing for inspecting welds, pressure vessels, pipes, and structural components. PUT enhances inspection reliability by allowing sectorial scanning, electronic beam steering, and multi-angle coverage without mechanical probe movement. Its ability to adapt focal laws and inspect complex geometries makes it especially valuable for modern engineering applications. According to ASTM E270020, phased arrays generate constructive and destructive interference through pre-calculated delays applied to probe elements, enabling electronic focusing and scanning. ASME Section 5 further recognizes PAUT as an acceptable method for weld examination, noting its flexibility and efficiency in encoded or manual scans. Additionally, ISO 185631-2022 defines verification and performance criteria for phased array instruments, ensuring that PUT systems meet specific functional and calibration requirements within frequencies ranging from 0.5 to 10 MHz. PUT principles and beam control, beam steering and focusing. Beam steering and focusing are core capabilities that differentiate PUT from conventional ultrasonic testing. Steering refers to the electronic manipulation of beam angles by altering time delays across transducer elements, enabling operators to inspect different orientations without repositioning the probe. Focusing is achieved by adjusting focal laws to converge ultrasonic energy at specific depths, enhancing sensitivity and defect characterization. Electronic steering simplifies coverage of weld bevels and complex geometries, while sectorial scanning, S-scan, displays multiple angles in a single view for comprehensive imaging. According to ASTM E270020, S-scans produce a swept-angle visualization that increases defect detection probability and coverage. ASME guidance further reinforces that encoded electronic scans improve reproducibility and allow for consistent operator-independent data acquisition. ISO 185631 specifies performance checks to ensure phased array instruments accurately deliver focal laws, steering precision, and consistent pulsing characteristics essential for reliable inspection outcomes. PUT scanning methods, sectorial and linear scanning. PUT enables two primary types of ultrasonic scanning, sectorial scanning, S-scan, and linear scanning, E-scan. Sectorial scanning electronically sweeps the beam over a range of refracted angles, producing a fan-shaped image that helps visualize defects at varying orientations. This technique is particularly effective for weld inspections, where discontinuities may occur at unpredictable angles. ASTM E270020 describes S-scan as an advanced method that provides richer data and improved flaw characterization. Linear, E-scan, techniques electronically shift the beam without altering its angle, mimicking a manual pass but with much greater consistency. ASME Section 5 acknowledges both techniques for encoded and manual scanning setups, highlighting PAUT's reproducibility advantages in standardized inspections. Meanwhile, ISO 185631 ensures PAUT instrumentation used for these scan modes meets functional performance metrics such as pulse shape, amplitude stability, and synchronization accuracy. Applications in weld inspection, weld evaluation and characterization. PUT is widely used for inspecting butt welds, T-joints, and other welded components across multiple industries. Its electronic focusing and multi-angle capabilities allow precise sizing of embedded defects such as cracks, lack of fusion, porosity, and inclusions. PUT often replaces radiography due to its increased safety, rapid results, and ability to perform in-service inspections without interrupting operations. ASME pressure vessel and piping codes highlight PAUT as a viable alternative to radiography, especially for welds exceeding 0.250 inches thickness, and emphasize its suitability for both fabrication and in-service inspections. ASTM E270020 further provides structured guidance for weld examination using phased arrays, ensuring coverage adequacy and appropriate scan plan development. ISO 185631 ensures that phased array instruments are properly verified for such weld applications, guaranteeing consistency in high-resolution defect imaging across automated and manual setups. PAUT Instrument Performance Requirements. Proper performance verification of PAUT systems is essential to ensure reliable inspection data. ISO 185631:2022 establishes requirements for phased array instrument characteristics including pulse shape, amplitude stability, probe element functionality, and signal consistency across channels. These criteria apply to both handheld and automated PAUT systems, helping operators confirm that equipment is functioning within acceptable tolerances before use. Verification ensures accurate beam steering, focusing, and imaging essential for characterizing discontinuities. ASTM practices emphasize that appropriate reference blocks and calibration procedures must be used to demonstrate equipment reliability on the specific materials and geometries being inspected. ASME Section 5 also mandates qualification of equipment and procedures when applying phased arrays, especially when deviating from traditional UT techniques. Advanced PAUT Techniques, FMC TFM and Advanced Imaging. Full Matrix Capture, FMC, and the Total Focusing Method, TFM, represent advanced data acquisition and processing techniques increasingly integrated into phased array systems. FMC captures all possible transmit, receive combinations across probe elements, while TFM reconstructs high-resolution images through post-processing algorithms. These techniques complement conventional PAUT by providing better defect visualization, especially for complex geometries and small flaw detection. Recent ISO developments, such as ISO 23865 and ISO 23864, outline procedures and requirements for applying FMC and TFM in ultrasonic testing, reflecting industry movement toward higher fidelity imaging and expanded applicability. ASTM and ASME codes continue to evolve to incorporate these advanced methods, particularly as equipment becomes more robust and computational capabilities increase. Combined with PAUT steering and focusing abilities, FMC/TFM greatly expand the engineer's toolkit for high-precision non-destructive evaluation. Overview of key UT/PAUT standards. Multiple standards govern the application of ultrasonic phased array testing to ensure consistency, reliability, and interoperability across industries. ASTM E270020 defines practices for performing contact PAUT on welds, including requirements for scanning strategies, calibration, and safety considerations. ASME Section 5 outlines rules and qualification requirements for applying phased arrays within boiler and pressure vessel construction and inspection. ISO 185631:2022 provides detailed specifications for PAUT instrument verification to ensure equipment meets performance thresholds. Additional standards such as ISO 7963, ISO 23865, and ISO 23864 address calibration blocks, advanced imaging, and array-specific techniques, ensuring global harmonization of UT and PAUT processes. Together, these standards form a comprehensive framework that guides practitioners in achieving reliable non-destructive evaluations using phased array techniques. Real-world PAUT implementation examples. PAUT has become a cornerstone technology for industries requiring high-reliability weld and component inspection. In oil and gas pipelines, PAUT enables rapid detection of lack of fusion and planar flaws without interrupting plant operations. In power generation, PAUT is routinely applied to pressure vessel welds, steam lines, and turbine components to detect service-induced cracking. Aerospace manufacturers use PAUT for composite inspection and structural metallic bonding assessments due to its ability to adapt focal laws and beam coverage to complex geometries. ASME-compliant PAUT has shown major advantages over radiography, such as eliminating radiation hazards, delivering near real-time evaluation, and improving detection of vertically oriented flaws. Additionally, advances in calibration standards and equipment verification per ISO requirements further strengthen inspection repeatability and regulatory acceptance. Implementation, calibration, and data analysis. Successful deployment of PUT requires proper calibration, wedge delay verification, sensitivity setting, and focal law validation. Operators must use appropriate reference blocks as specified in standards such as ISO 7963 and ASTM E270020 to ensure accurate measurement of system response. Detailed procedure qualification is required under ASME Section 5, especially when adopting novel PUT scanning techniques. Additionally, ISO 185631 establishes verification workflows for instrument performance, ensuring that internal electronics, multiplexer channels, and pulsar receiver functions meet defined tolerances. Proper data interpretation using A-scan, S-scan, and merged views is essential to accurately characterize defects, and encoded scanning provides comprehensive traceability and reporting. These measures collectively ensure consistent and repeatable inspection outcomes. Summary and best practices. Ultrasonic phased array testing, PUT, provides engineers with a powerful, adaptable, and highly reliable inspection technique for evaluating welded structures, pressure systems, and complex components. Through electronic beam steering, focusing, and high-resolution imaging methods, PUT significantly enhances flaw detection and characterization across various industries. Adherence to standards such as ASTM E270020, ASME Section 5, and ISO 185631 ensures consistent, high-quality inspections and regulatory compliance. As technology continues to advance with methods such as FMC and TFM, PUT will play an increasingly important role in ensuring safety and structural integrity across demanding engineering environments.